All right, today we are diving into a massive cosmic cold case. We're talking about the mystery of our own existence. And it turns out our main clue might just be a tiny, incredibly elusive particle that holds the secret to, well, everything. So let's start with the biggest question of all. Why are we here? And I know, that sounds more like philosophy than physics, right? But it's a genuine scientific puzzle. According to our best theories, the Big Bang should have created a universe with, well, with nothing in it but leftover energy. The fact that we're here at all means something, somewhere, broke the rules. The real question is, what?
And believe it or not, the key to this entire cosmic mystery, the one clue that could explain why anything exists at all, might be hidden in the bizarre life and death of a single, fleeting, subatomic particle.
To crack this case, we have to rewind all the way back to the very first moments of the universe. See, the Big Bang should have produced perfect symmetry. For every single particle of matter, the stuff that makes up galaxies, stars, you and me, it should have created an equal and opposite antiparticle of antimatter, a perfect mirror image. But here's the twist. When a particle of matter bumps into its antiparticle twin, they annihilate each other in a flash of pure energy. Poof, gone. So if they were really created in a perfect one-to-one balance, they should have wiped each other out completely, leaving a universe filled with nothing but light. The very fact that we have galaxies, planets, and people is the ultimate proof that this symmetry was broken. Somehow, for every billion pairs that annihilated, just one extra matter particle was left over. And that tiny, tiny imbalance is the reason everything we see exists. Physicists call this the baryon asymmetry problem. So, how do you even begin to investigate a cosmic crime of this scale? Well, you follow the evidence. And our star witness, our main person of interest, is the B Meson. It's a particle made of even smaller building blocks called quarks. In this case, it has a heavy bottom quark paired with a lighter anti-quark. And the way this one specific particle lives and dies, that behavior is our absolute best clue for solving the universe's greatest mystery. You see, a B Meson is not built to last. It exists for only about 1.5 trillionths of a second before it decays or falls apart into other particles. Most of the time, its bottom quark changes into a charm quark. You can think of this as the main highway, the B to C transition. It's the well-traveled road. But every once in a while, it takes a much rarer path, decaying into an up quark or a strange quark. These rare decays, these are the hidden back roads of the particle world. They are incredibly hard to spot, but that's where the biggest secrets about the universe's imbalance are hidden. So how on earth do you study something so tiny and short-lived? Well, you basically perform a kind of high-tech particle forensics. First, inside massive particle accelerators, you smash beams of particles, like electrons and their antiparticles, positrons, together at almost the speed of light. This explosion of energy creates a shower of new particles, and in that shower are our B mesons. Step 2, the hard part. You have to isolate the one B meson decay you're looking for from literally billions of other uninteresting events. It's like finding a needle in a cosmic haystack. And finally, you reconstruct the crime scene, working backward from the debris, the decay products, to figure out exactly what happened. And our particle detectives have two main ways of doing this. In one type of experiment, you create the B meson so they're almost standing still. This gives you a really clean crime scene, making it much easier to see exactly what they decayed into. The other approach, at super high energy colliders, creates B mesons that are zipping along at incredible speeds. Now the scene is a lot messier, but because they're moving so fast, you can precisely measure the particle's lifetime. Each method gives you a totally different kind of clue. And the very first major clue was a real shocker. Scientists expected the B meson to vanish almost instantly. Instead, it lived for about 1.5 picoseconds. Now that sounds impossibly fast to us, but in the world of subatomic particles, that's an eternity. This shockingly long lifetime was a huge hint that the connection between this family of heavy quarks and the lighter quarks was way, way weaker than anyone had predicted. But wait. The B meson had an even bigger surprise up its sleeve. Get this. Scientists discovered that a B meson can spontaneously transform into its own antiparticle, the anti-B meson, and then back again, oscillating billions of times every second. It's a quantum mechanical identity crisis of epic proportions. This phenomenon is called BB bar mixing. And this is where the B meson really showed off its detective skills. The speed of this back-and-forth oscillation was way faster than the theories at the time could explain. It turns out, this flickering is enabled by other virtual particles popping in and out of existence for a fleeting moment. And the frantic speed of that oscillation told physicists that one of those fleeting particles, the top quark, had to be unbelievably heavy. We're talking long before any experiment was powerful enough to actually find it directly. The B Meson predicted it. The next big break in the case came in 1993. An experiment finally saw something they've been hunting for years, an incredibly rare event called an electromagnetic penguin decay. And yes, that is its real name. I'm not making that up. This discovery was massive because it wasn't just another decay path. It was a whole new type of process. It gave us a direct window into the strange quantum machinery that drives these transformations.
Now, all of these clues, the long lifetime, the rapid mixing, these super rare decays, they're all pieces of a much larger puzzle. They help us fill in this chart, which is known as the CKM Matrix. Okay, it looks complicated, I know, but just think of it as the official rule book for how quarks can change from one type to another. Each of those little boxes represents the probability. And B Meson decays are our single best tool for figuring out the numbers in this rulebook, especially the most mysterious and unknown values.
And here's the ultimate goal of this entire detective story. If we can measure all these decays and figure out the values in the CKM rulebook in many different ways, we can start to check if the rulebook even makes sense. It's like checking the math. If we measure the same value from two different B Meson decays, do we get the same number? If we don't, it means our rulebook is incomplete. It would be a flashing sign that there's new physics out there beyond everything we currently know. This all comes together in the final test, the unitarity triangle. According to the standard model, if you plot several of these crucial CKM measurements on a graph, they absolutely must connect to form a perfect closed triangle. No gaps, no overlaps. And thanks to the B Meson, we can measure all three sides and all three angles of this triangle independently. But here's the most critical part. The area of that triangle is a direct measure of the asymmetry between matter and antimatter. It's a measure of the very thing that allows us to exist. So we make all the measurements. Do they connect perfectly? If they don't, if the triangle fails to close, we've found our smoking gun. We've found proof of physics beyond the standard model. For decades now, the B Meson has been our indispensable guide. It pointed to the massive top quark, it's helped us map out the fundamental forces, and it gives us our most rigorous test of the standard model. So far, all the measurements show that the triangle does in fact close. But as our experiments get more and more precise, tiny cracks in that perfect picture might begin to show, hinting at a much deeper story. The cosmic detective story is far from over.